These are the human vocal cords, and that's the sort of weak sound they'd make if you could somehow remove them from the body and yet persuade them to keep on working. It's remarkable that such rough sounds can be transformed into something as pleasing as this. What we're hearing is the output from a very sophisticated signal processing system, the human voice. In this program, we'll be taking a look at the mechanism that produces the human voice, and we'll use this as a step on the way to understanding how that most useful of human sounds is built up, speech. We'll be doing this for two reasons. The first, and perhaps most important, is that it will give us a chance to use those ideas you've learned from Unit 4. That is, to think in terms of the frequency components of a signal instead of just in terms of variations of amplitude with time. Look here. This is the time-varying waveform of my voice, amplitude against time. You can see about a quarter of a second's worth here. Fi, fi, fo, fum. It's possible for me to freeze that waveform, and I'll do it with just one sound. Ready? Ah. Now compare it with this.
Ah.
Well, they're both time waveforms of the same sound, but because they're different voices, there's not much similarity between them. Even a speech expert couldn't spot that they were the same sound if he had to use traces like these. To make headway with understanding speech, we need to adopt an alternative way of looking at these signals. That is by analysing them into their frequency components. But now, down to basics. Let's revise what we mean by frequency analysis. In the last TV program, you saw how David Creecraft was able to make this square wave by adding together a series of sine waves. And this is the equipment he used. This switch here gives me the fundamental, it's around 500 hertz. And in addition, I can get frequencies of 3 times the frequency and 1/3 the amplitude, 5 times the frequency and 1/5 of the amplitude, and 7 times the frequency and 1/7 the amplitude. This is getting quite small now, but if I now go back and add in all those other components, you can see I end up with a pretty good square wave. I've taken care to get the phases of all these components with these knobs here. In fact, we're doing electrically what was done mathematically in the text with the Fourier series. So adding sine waves together works in reality as well as it does on paper. Now, this particular equipment limits me to just adding a fixed number of frequencies together. But don't go away with the idea that we're somehow limited to just these few frequencies. You'll soon see that to get the sort of complex waveform that we meet in practice, we have to add many more components than we have here. Now, we know the components of this particular waveform because we've just built it up from scratch, but we're usually presented with the problem the other way round. We're normally presented with a signal like this, and we've got no idea of the components that went into it. How would you go about analysing the waveform and finding out what components it was made from? Well, one answer is to use a device like this. It's called a spectrum analyzer, and it's easy to see what it does. Look, I have a sine wave generator here, and if I connect it to the input of the spectrum analyzer, you'll see I get a single line. Now, if I vary the frequency of this sine wave, that line moves, first decreasing frequency, and then increasing frequency. If I now change the amplitude of that sine wave, increasing and then decreasing, you can see that the length of the line alters. So we're plotting frequency along this axis and amplitude in this direction. It's plotting the spectrum of its input, in fact, just a single line for a sine wave. Well, that's okay for a sine wave. Let's now have a look at that square wave. There, the equipment has now analysed it into its components, the fundamental, the third harmonic, the fifth, and so on. And they're all going down in amplitude, just like we know they do. So this machine has actually managed to give me most of the information I needed to generate that square wave in the first place. It's given me the amplitudes and the frequencies of the components. But it hasn't given me quite all the information about the spectrum. There's one bit of information missing. Can you remember what it is? Right, well, there's no phase information here. Remember that when we specify a spectrum precisely, as well as knowing the frequencies and amplitudes of the components, you've got to know their phases. But I won't be worrying too much about phase in this program, And that's all right when you're looking at speech signals, as I'll show you later on. But we can't always afford to ignore phase information. In a video signal, for example, the phase information is important in conveying the color. So if you get the phase all wrong, the effect can be a bit disturbing, particularly if you're watching on a color set. So don't get the idea that phase doesn't count. It's only when we're dealing with speech that we can generally ignore it. Right, with the revision out of the way, let's go down to what we started out to do, to look at speech and the human voice in the frequency domain. Remember those vocal cords? They produce a signal which in the time domain looks like this. But what does this look like in the frequency domain? Well, there's a whole lot of components falling off in amplitude. So with all these frequencies, can you see how they might be able to generate a melodic note? Well, to explain how that all works, here's Mike Ashby from University College London.
Well, you've probably guessed by now what must be happening between the vocal cords and the outside world. Somehow, particular frequency components in the sound from the vocal cords are being amplified, while others are being rejected. In other words, it's an example of filtering. The sound from the vocal cords is the input to a filter, and it's the output of that filter that we hear as speech. Obviously, it must be some kind of acoustic filter. Let's have a look at how it works. Down here are the vocal cords which vibrate, as we saw, when air passes up between them from the lungs. Above them here is a tubular cavity, the pharynx. We can change the shape of that a little by the muscles in its walls here. The pharynx leads to a second cavity here, the mouth cavity, and the shape of that is very variable depending on what we do with the tongue and the lips. And if this little flap here, which acts as a valve, is open, then the air in these two cavities is coupled to the air in yet a third cavity, the nasal cavity. Now, the vocal tract cavities are able to filter the sound from the vocal cords because of the phenomenon known as resonance. Here's an example of a cavity, a simple example, an ordinary coffee mug. If I deliver an input to this mug, we hear a note, a particular note, which is due to the resonant frequency of this enclosure. And if I change the resonant frequency of the enclosure, we hear a different note because I've changed those components selected by the cavity from the energy in the input. In fact, I can do exactly the same thing with my vocal tract, delivering a shock of energy to my vocal tract by flicking down here by my vocal cords. I can set the vocal tract resonances ringing. Well, Chris has another example of resonance.
Well, what I was doing there was using my lips in exactly the same way as you use the vocal cords to produce a sound. And the output from it was going into this piece of hosepipe and a funnel, which I was using as a resonant cavity. So a rather harsh sound I was producing at the input, like this, was being transformed into something quite nice. Well, I thought it was anyway.
Well, so far then, we know we're dealing with an acoustic filter, and we've seen a couple of examples of acoustic resonance. Of course, the vocal tract, unlike a coffee mug or a piece of hosepipe, is capable of being changed infinitely in shape. In fact, during speech, the shape is continuously in motion. It's continuously being altered, and so the filter characteristics are being altered all the time as well.
Of course, Mike was talking about acoustic filters, but you're probably more familiar with electronic filters. These allow some frequencies to pass through and they suppress others. The RC circuit in your home experiment kit is a good example. The amplitude response of an RC filter can be drawn as a bode plot like this. Remember that the vertical scale is logarithmic, measured in decibels. Well, that's a simple low-pass filter, but it's possible to build much more sophisticated filter circuits with other characteristics, for instance this. The circuit which has this response will only allow frequencies around 1 kilohertz through without attenuation. But now let's put in a wave with some more components, that vocal cord waveform, for instance, where the amplitudes fall off at about 12 decibels per octave. Now, if we passed this through the filter, we'd get this at the output. Notice now how the band of frequencies around 1 kilohertz has been emphasized. By modifying component values in the filter circuit, we can actually shift the position of the peak up or down in frequency, and so mimic the changes in size of the vocal cavities, which you remember alters the position of their resonant peaks. So if we can do that, we might be getting close to electronically synthesizing the human voice.
Well, we're getting warm, but the vocal tract is a complicated set of cavities, and it shouldn't be too surprising to find that it doesn't just have one resonance, it has a whole set of resonances. So that means we're dealing with a filter which has not just one peak in its characteristics, but a whole set of peaks. In fact, in the frequency range up to 4 or 5 kilohertz, there are usually some 3 or 4 peaks that are of importance. Let's have a look at some spectra. Here we have the spectrum for the vowel R, as in start, amplitude against frequency. The input for this sound from the vocal cords is a harmonic spectrum going down at 12 dB per octave, roughly, as we saw. But that input has been through the vocal tract filter with its resonances, and as a result, we see in the output the peaks in that filter's characteristic. Here's one of them, here's another, and here's a third. If we look at a different vowel, the vowel E, as in feed, well, it's the same input, exactly the same input, but the vocal tract is in a different position and the peaks have moved to new frequencies. Here's one of them, here's the second, and here's the third. And for a third different vowel, the vowel oo, as in food, well, we know what to expect, the peaks again in different positions. So the differences in spectrum, and hence the differences in sound among these three vowels, are due to the different positions of the peaks in the vocal tract characteristic. The input is the same for each of them. In speech work, we have a name for these peaks. We call them formants. And starting from the one of lowest frequency, we label them formant 1, formant 2, formant 3, and so on.
Well, I haven't got a filter here with 4 or so peaks, but I've got one with just 2. And even so, it certainly gives voice-like sounds. Its inventors call it a chatterbox. Let's see how it works. It's got 2 filters in cascade, each with just 1 peak. So the overall frequency response is going to have a 2-peak characteristic. And I'm going to feed in a stream of pulses to the input. That's to simulate the excitation produced by the vocal cords. Now, if I move the joystick this way, I can vary the position of one of the peaks. And if I move it this way, I can control the position of the other peak. So, by wiggling it around, I can vary both peaks. So when I move the joystick, I'm partially simulating the sort of thing that might be going on in the human vocal tract as the resonances change. Well, it sounds extraordinarily voice-like, but it's going to take me a lot of practice before I can get this thing to talk.
Well, it would take a lot more than practice, because so far we've only considered one type of speech sound, the so-called voiced sounds like R, E, and oo. There's another important category of sound in human speech, the unvoiced sounds like F and S. Now, these don't use the vocal cords. They rely instead on the turbulent flow of air through a narrowing in the vocal tract. For example, in the sound F, what I do is make a narrow gap between the upper teeth and the lower lips and blow air through that gap. The airflow becomes turbulent with a consequent generation of noise. Let's look at the spectra of some of these unvoiced sounds. Here's the spectrum of the sound S at the end of the word niece. No sign of discrete frequency components in this spectrum. We're dealing with a continuous spectrum. That's why we've relabeled this axis. Look back to your text to see just why. The filtering situation for these unvoiced sounds is a little more complicated. It's not too easy to see where the formants are in this spectrum. Another thing to notice is that the energy goes on to high frequencies. In fact, if we looked further up the frequency scale, we'd find that the energy continued. But it is true that one sound differs from another largely in terms of spectrum shape. Here's the sound sh at the end of the word lush, another continuous spectrum, but different in shape from the one for S. And here, a third unvoiced sound, the F at the beginning of fear, a different spectrum shape again. So, to produce a satisfactory speech synthesizer, we need the ability to copy these unvoiced sounds as well. And that means generating a spectrum crammed full of frequency components.
Well, in the text of Unit 4, you learnt about just such a spectrum. Wonder if you can remember what it was. Well, white noise, you'll remember, contains a whole range of frequencies. This is what it sounds like and what it looks like in the time domain. And if we look again to the spectrum analyzer, it looks like this. An almost flat frequency spectrum. Well, normally in electronics, we do our best to get rid of noise. It's a nuisance. But in speech synthesis, we put it to good use in generating the unvoiced sounds that Mike was talking about, the sh, the s, and the fs. So by passing white noise through filters which attenuate the right frequencies, we can shape or mold this flat spectrum into the forms that Mike had just now. I've got 3 on the chatterbox, for instance. But no matter how I practice trying to make it talk, I'll never get as good as this.
Hello? Hello? How are you? Hello? How are you? You? Me? Me? You?
Well, that was an example of synthetic speech from University College London. It used basically the ideas we've been talking about, plus a few more sophistications to make it sound more natural. To produce speech like that, we have to be continuously varying something like 16 or so parameters: the pitch, the formant frequencies, the noise amplitude, the noise spectrum, and so on. We saw what difficulty Chris had in manipulating just a few parameters, and it's beyond the capacity of a human operator to move all 16, so we rely on a computer to do the job for us. We have such a system at University College. We use it for research on speech perception. Mark Huckvale explains how it works.
The instructions for controlling the synthesizer are input to the computer via the terminal here. They're then stored within the computer, which can send them out to the synthesizer at the correct rate. Now, the synthesizer is just a bank of filters which are movable in frequency and amplitude, and a pulse generator and a noise generator. Now here I'm trying to set up a set of control instructions for the synthesis of the sound A. A. Now for the synthesis of more ordinary words, the control instructions are much more complicated. And to produce good quality speech, we have to update the 16 parameters of the synthesizer every 5 or so milliseconds, and that's a lot of information.
But speech synthesis isn't just a matter of stringing together a set of stock sounds. We saw how to make the sound A. Mark had to have the formants in motion. One sound flows naturally into the next, and one word flows naturally into the next. Just look at the spectrum of my voice as I pronounce one word. Noise. Noise. You see, it's constantly changing for all the reasons we've been talking about. How do we analyze this constantly changing pattern to get the information we need to control the synthesizer? Well, we need to store it somehow. At one instant, the spectrum might look like this. 50 milliseconds later, like this. 50 milliseconds later again, like this. And so on. Noise. Noise. that information can be represented in three-dimensional form. Here it is, frequency against time for the word noise. Here's the here the oi, and here's the z, the z at the end. We can see very clearly how the formants change through the word. Let's take the second formant beginning here. It grows in amplitude and goes down a little in frequency. Then it begins going up in frequency and also growing in amplitude. And then here it's coming down in frequency again and down in amplitude. And for the Z at the end, we can see how all the energy is at the high frequency end of the scale. There's virtually nothing down here at the low frequency end. But this kind of presentation is rather bulky. After all, if you were going walking in the Lake District, you wouldn't take with you a model of mountains and valleys. You'd take a map. This is a map, if you like, a speech map. We call it a speech spectrogram. Frequency against time. Once again, we can see very clearly how the formants change throughout the word. Here's the second formant we were just looking at. It's by studying patterns of formant flow from spectrograms like this that we derive the control signals we need to drive the synthesizer. But we don't work with spectrograms of this size. They're produced on a more manageable scale.
This is a spectrogram of the word goldfish. And I'm going through it step by step to get a set of the filter frequencies and amplitudes as they move in time. Here I'm looking for the important changes as well. And here from the I to the sh part of fish. Now this information could be sent to the computer, which ends up controlling the synthesizer.
Goldfish. Goldfish.
So I think you'd agree that in looking at the speech signal and the human voice mechanism in the frequency domain, we've been able to advance quite a long way. And it does illustrate the power of the approach demonstrated in the text. Just one last point though. I touched on it at the beginning of the program. It's to do with this question of phase. Let's go back to the synthesized square wave. As you know, the phases of the components are critical for producing a square wave. If I alter the phase of one of these components, the shape of the waveform changes quite dramatically. Now let's listen to the effect of that shape change. Now you see what I mean about phase being unimportant? There's absolutely no change in sound at all. That illustrates a basic property of the human ear. It's less sensitive to the phases of the spectral components than it is to their amplitudes and frequencies, and that's why we haven't been worrying about phase throughout the program. Right, having looked at the speech signal in the frequency domain, we should now be in a position to specify the bandwidth of a system which has to handle speech. Mike showed us that the frequencies of the unvoiced sounds go way up above 5 kilohertz. So to transmit good quality speech, like you're receiving at the moment, the system has to cater for all these higher frequencies. But we don't necessarily need such a wide bandwidth to retain the intelligibility of speech. We speak on the telephone regularly, with little trouble in understanding, even though here the bandwidth is limited to frequencies between about 300 hertz and 3.4 kilohertz. So the moral is, when you're deciding on the bandwidth, it's not only necessary to know which frequencies are there, you've also got to know which ones are important.